Hi and welcome back. Continuing our discussion on state minimization, we'll look at a formal algorithm to do state minimization in this video. So I already have the algorithm written right here. So the first step is that initially all state pairs are unmarked. So what we are going to do is we are going to form state pairs. So Q0, Q1 will be one pair and Q1, Q2 will be another pair and so on. There will be all pairs of states whether they are connected or not. So Q0 will be paired with Q1, Q2, Q3, Q4, Q5, all of them. So the next step is, so in the first step itself, we are saying that no state pair is marked right now. And what we mean by marking is we are saying that when we mark a pair, we are saying that these two states definitely cannot be equivalent. So the very next step is for every pair Q1, Q2, mark the pair if Q1 is final and Q2 is not, or vice versa. In the previous video, we already saw that any two states for which one of them is final and the other is not cannot be equivalent. So in the second point, we are doing exactly that. We are saying if one of them is final, the other one is not, mark them with a cross. These cannot be equivalent. And we do this for every pair. The third point says repeat until we cannot mark anymore. So the third point is something that we are going to do over and over again. So we say if there is an unmarked pair Q1, Q2, so the pair Q1, Q2 hasn't been marked yet, then mark the pair if delta of Q1, A is delta of Q2, A is marked. So we are saying that let's say we have two states Q1 and Q2 and on some input let's say 0, they go to a state which is marked and when we say that they go to a state pair which is marked, then we are saying that the transitions that they are making are definitely not equivalent. So in that case, these two states also cannot be equivalent. And it's alright if you haven't understood the algorithm completely. What we'll do now is we'll take a look at the DFA that we saw in the previous video itself and we'll try to perform this algorithm on that DFA. So first I have my Q0 which is the start state and this on 0 goes to Q1, on 1 it goes to Q2 and both of these on a 1 they go back to Q0. On 0 Q1 goes to Q3 and Q2 goes to Q4 and Q3 and Q4 on a 0 they just retain state and now on 1 they go to a final state which is Q5. So I have Q5 right here. This is the DFA that I have and I want to do the state minimization on this. So what I'm going to do is I'm going to create a table. So I have a table right here where I'll have the states. So I have Q0, Q1, Q2, Q3, Q4 and Q5. And on the vertical axis as well, I'll have the states. So I have Q0, Q1, Q2, Q3, Q4 and I'm kind of out of space here, so let's just decrease the size of our DFA first. So I'll make some space right here by reducing the size and here as well let's just take this entire thing and move it up. So I have Q5 right here and this is the table that I've got. I'm only going to be using half of this table because the other half is just a repetition. So let me just cross that out first. So I'm not going to be using this part at all. So I don't need any of this. So I'm just going to be using the lower triangular part of this. And now let's start with our marking. So let's first just mark that Q5 is my final state. So I've written it down there. And now the first step that I need to do is initially all of them are unmarked. And now what I do is for every state pair, I see whether one of them is final, the other one is not. If that's the case, then I want to mark that. So I have Q0 and Q1, both are non-final, so that's fine. I have Q0 and Q2, both non-final. Q0 and Q3, both non-final. And when I get to Q0 and Q5, I know that one of them, Q5 is final, Q0 is not. So I can mark this right here. And I can do this for all of the other states as well. So I've marked all of these. So Q5 and Q1 cannot be equivalent either. So I've marked it accordingly. And now what I do is I move to the third step. Now this is the important step. So what I say is from my Q0 and Q1, these are the ones that I'm comparing. So let me just mark that. These are the ones that I'm comparing right now. And now what I say is if there's any transition for Q0 and Q1 where if there's any symbol for which Q0 and Q1 go to some state pair which is marked, then I need to mark those. So where does Q0 go on a 0? It goes to Q1. And where does Q1 go on a 0? It goes to Q3. So I need to check whether Q1, Q3 is marked, and that is right here. And it's not marked, so I cannot comment anything based on the 0 transition. Now let's look at the 1 transition. So where does Q0 go on a 1? It goes to Q2. Where does Q1 go on a 1? It goes to Q0. So I check whether Q0, Q2 is marked. So that's right here. It's not marked. So I cannot comment anything at this point about Q1 and Q0 and Q1. And I can do the same operation for all of the states. Now, when I come to Q1 and Q3, I can see that on 1, Q0 goes to Q2 and on 1, Q3 goes to Q5. Now, Q2, Q5 is this thing right here which is marked. So I can definitely say that Q0 and Q3 are not equivalent. So I can mark across here. With the same logic, I can also say that Q0 and Q4 are not equivalent. So I can mark this now. And at this point now, what I can do is I can again check for Q1 and Q0 and Q1 maybe. So no, at this point it's not possible for me to check for Q0 and Q1. So next what I do is I check for Q1 and Q3. So on 1, Q1 goes to Q0 and on 1, Q3 goes to Q5, and I can see that Q0 and Q5 are marked right here. So I can now mark Q1, Q3, which is this one right here. Similarly, let me do it for Q2 and Q3 as well. So on Q2, I go on a 1 to Q0. And on Q3, from Q3 on 1, I go to Q5. Now I get the pair Q0, Q5, which is again marked. So I can say that Q2 and Q3 are also not equivalent. So I can mark this as well right here. And next what I can do is I can perform the same operation for Q1 and Q4. So I'm going to get Q1, Q4 as not being equivalent. and I'm also going to get Q2 and Q4 as not being equivalent. So let's cross both of these out. So at this point now, what I have is I have this right here, Q0, Q1, I have Q0, Q2, I have Q1, Q2, and I have Q3, Q4, which are still unmarked. So what I do is for Q0 and Q1, I can now check. So on 0, Q0 goes to Q1. So let me just write it down here. Q0 goes to Q1, and from Q1 on 0, I go to Q3. So what I need to check is whether this pair is marked now. So I check whether Q1, Q3 is marked, which is right here. So it is marked, which means that I can also mark Q0 and Q1. So let me just do that. So I mark this as well. And similarly for Q0 and Q2, from Q0 on 0 on 0 I go to Q1, and from Q2 on 0 I go to Q4. So if Q1 and Q4 is marked, which it is, then I can mark Q0 and Q2 as well. So I mark this, which now leaves me with these two right here, which is Q1, Q2. So let's check for Q1, Q2. So Q1 on 0, let me get rid of this, and Q1 on 0 goes to Q3, and Q2 on 0 goes to Q4. So if Q3, Q4 is marked, then I can mark Q1, Q2 as well. But Q3, Q4 is not marked, so I cannot comment anything on a 0. Next, what I check is from Q1 and Q2, both of them on 1, I go to Q0. So I have Q0, Q0, which is never going to be marked because I'm never going to say that Q0 is not equivalent to Q0. So for both transitions, Q1 and Q2, at least right now, appear to be equivalent. So I cannot comment anything on Q1, Q2 right now. Next, let's look at Q3, Q4. So Q3, Q4 on 0, the pair that they go to is just Q3, Q4 again. So if Q3, Q4 is marked, I can mark Q3, Q4, but Q3, Q4 is not marked. So I cannot mark Q3, Q4 right now, at least based on a 0. Now looking at 1, from Q3 on 1, I go to Q5, and from Q4 on 1, I go to Q5. So once again, I'm never going to say that Q5 is not equivalent to Q5, so I cannot mark Q5, Q5. So at this point, I cannot comment on Q3, Q4 either, and that was the only two squares that I was left with in my table, which was Q1, Q2 and Q3, Q4. And for both of these, I cannot comment anything on marking them right now, so I cannot mark both of these squares. So what happens at this point is, because I cannot mark anything more, then I take whichever are unmarked and I can merge those states. So I can merge Q1 and Q2. So what I'm going to get after my state minimization is that Q1 is equivalent to Q2, and I'm going to get Q3 is equivalent to Q4. So these are the two equivalence conditions that we've got for the DFA on the left, and this is what we saw in the previous video as well. So the minimized DFA that I'm going to get is something like this. I have Q0 from where I can go to Q1, Q2, from where I can go to Q3, Q4, from where I can go to Q5, which is a final state. So this is the DFA that I'm going to get, and I can now write my transitions accordingly. So I remember that this goes to itself on a 0, it goes to Q5 on a 1, this would be on a 1, and actually this would be on a 0. On a 1 this would just come back to Q0, and from Q0 it goes to Q1, Q2 on a 0 or a 1, and Q5 just loops to itself on a 0 or a 1. So this is the state minimization algorithm. This right here is my algorithm which I implemented with this table right here. So this is how the algorithm is implemented, and this is the DFA that I get after I've performed the algorithm on the given DFA. So before we conclude this video and our discussion on state minimization, I just want to mention a few points. So the first one is which method is best for state minimization, whether we should do it intuitively, whether we should use the algorithm. So if you've got enough practice with it, go for the intuitive one, because that might be faster than making the table. But the algorithm is going to give you a sure shot solution. There is no chance that the algorithm is going to go wrong. So if you want that, you can go with the algorithm. But there is a third option which I would say is the best one, which is to just draw the DFA in JFlap and look for state minimization. JFlap has an option for state minimization, and that just gives you the DFA within a few seconds, no matter how big the DFA might be. So that's the best way to do it. And another thing that I want to mention before we end this video is the condition where we say that two states are equivalent. There is a formal condition where we say that two states are equivalent. So Q1, Q2 are equivalent if and only if Q delta hat of Q1, X is accepted and delta hat of Q2, X is accepted. So actually, instead of this and, I should probably have another if and only if here. So what this says is, and I should also add for all X belonging to sigma star. So what this statement says is that if I have two states, then those two are equivalent if given any string. If starting from one state and that string, I end up with an accepting state for both states. So I have, let's say, Q1 and Q2, and I'm given a string X. Then I start from Q1, I take X, and I reach a final state, and from Q2 I start with X and I reach an accepting state. So if I reach an accepting state in both of them, or if I reach a rejecting state in both of them for all strings X, then I can say that both of my states are equivalent, and whatever intuitive or algorithmic procedure that we have performed to do state minimization conforms to this statement right here. So I just wanted to put this point out. So these are equivalent if this condition holds. And that's it for this video, and this ends our discussion on state minimization. Hope you're able to understand state minimization from these two videos. If you have any questions, put them in the comments below, and do give the videos a like. I'll see you next time.